First two videos from today were very dense, so I'm going to try and keep the third video as short as possible. And we're going to talk about capturing deviations from ideal behavior in mixtures in this video. So we'll start kind of how we went in the last video. We'll talk about the real solution first. And to capture the deviation, we're going to use the concept of an excess property. So remember, I defined this for like excess molar volume, for instance. Excess is equal to the real property minus the ideal property. So again, capturing deviations from ideal behavior. So in this case, what we've got is the excess chemical potential. And this is going to be a function of Tp and x is equal to the real chemical potential. That's just regular old mu I, Tp and x, minus mu for the ideal case as a function of Tp and x. And recall that in the last video, I talked about how to calculate what the ideal solution chemical potential is. That was simply minus G under bar, so that's the molar Gibbs free energy, component I, plus RT ln of x. This is the one that we didn't derive, but I showed you where you could see the derivation if you were interested. Now the real chemical potential, we're going to use that same equation that we used before. Molar Gibbs free energy plus RT ln of the mixture fugacity of component I as a function of Tp and x. We have to move that over a little bit over the pure component fugacity. Whoops. Fi of T and P. All right, and we're going to say that is equal to the excess chemical potential. All right, so for the ideal solution, the molar Gibbs free energies can cancel out. So those are gone. And what we're left with is just the RT ln terms. And actually, this has got to be a parenthesis such that that's a minus as well. So again, property of logarithms is that when you subtract two terms in logarithms, you can put one over the other thing. So this xi can go into the denominator. So I can simplify this by saying RT ln of mixture fugacity of component I is a function of Tp and x over xi fi is a function of T and P. And in order to simplify this, this is what we are going to define as our activity coefficient. So this is defined as gamma I. So this is something that I introduced in Monday's video, and this is kind of showing you where it comes from. Define f hat I function of Tp and x over xi fi equals gamma I as the activity coefficient. And I introduced this already too, but when gamma I, remember in the modified Raoult's law, if gamma I is equal to 1, it cancels back to the ideal case. So in this equation, if I've got ln of 1, that is 0, which makes this entire term 0. And I've got the excess chemical potential is 0, meaning that the real chemical potential is equal to the ideal chemical potential. All right, so that is the ideal solution. Next, we'll talk about the ideal gas. And for the ideal gas, we've got something similar, just a little bit different. For the ideal gas, we're going to use a departure function, and in the notation of Dahm and Visco, they like to call it a residual property. So for them, they say that their chemical potential residual property, this is also known as our departure function in the Sandler textbook, is a function of Tp and y is equal to mu I. This is the real property. So a departure function is kind of similar where it's real minus ideal. So mu I, Tp, and y minus mu I, ideal gas, Tp, and y. And similar thing here. So we already know what our ideal gas is from before. So that's minus molar Gibbs energy of an ideal gas plus RT ln of y, I. And our real is also defined before, molar Gibbs energy plus RT ln of mixture fugacity Tp and y over pure component fugacity, function of Tp. And in this case, we cannot say that the molar Gibbs energy and the ideal gas Gibbs energy just cancel. And that is because it's possible that our gas has a deviation from ideal conditions itself. So we had no such constraint in our ideal solution, but consider the fact that the gas may be at a high pressure. So at 10 atmospheres, for example, my real solution is not going to have the same molar Gibbs free energy as the ideal gas would. So therefore, we need to look back in order to find what the departure function is. We can't cancel these things out. So we have to say that the residual property or the departure function, this function of Tp and y is, so I just wrote that simplified quickly. And then I can't remember if we talked about this before. I want to say that we did. This departure function of Gibbs free energy between the real case and the ideal case, that can be rewritten as RT ln of phi. So remember this phi, well, I'll write it in the expanded form first. Remember that this was our phi. But anyway, when we have this simplification now we've got RT ln terms in both, so we can combine, we can factor out the RT and then combine what is inside the ln term. So completing that step, I'm just going to write it. Just made a little mistake here. This has got to be ideal gas up there, which simplifies to yi times p, as we talked about in the last video. So therefore, when I combine these two expressions, wait a minute, no, yi times fi, t and p. So when I combine these two expressions, I get some cancellations that are occurring. So this fi is going to cancel with that fi, and I'm going to be left with this expression. Now this expression is unwieldy, so we're going to do something similar where we define the term inside the ln as another type of activity coefficient. But this one is going to be our phi hat. And this is the mixture fugacity coefficient of component I. Mixture fugacity coefficient. And similarly to the activity coefficient, when this is 1, we've got ln of 1, and that's 0. So the real property, or the residual property, is going to be 0, meaning that the real property and the ideal property are identical. So when we have ideal behavior, ideal gas behavior, this mixture fugacity coefficient is 1, and things cancel. So that's going to be all for today. Next time we'll use these two terms, so the two activity coefficients, and we'll talk about what is called gamma phi modeling. And hopefully we'll get to some examples, because I know that real heavy derivation type days like today are kind of boring, and it's difficult to see where you'll use stuff like this. I'll try and give us some examples to get some applications of this material. See you next time.